Welcome back to this course on advanced memory hierarchy design. In this lesson I will give a quick recap of the basics of caches. I already described the basics of caches in course 1, but it is important that the basics are well known and I therefore quickly repeat them in this lesson. Let's now quickly review the basics of caches. There are 4 basic questions that need to be answered. The first question is, where is a block placed in cache? Recall that any cache consists of a number of sets. A direct map cache is a special case of a set associative cache where the sets are singletons. That is, each set consists of a single element. To determine the set onto which a block is mapped, we first need to determine the block address, which is given by the byte address divided, integer division, by the block size. Then the block is mapped to the set with index block address modulo the number of sets. The second basic question is, how do we find a block? Recall that every cache block has a tag, which is the portion of the address that is not implied by the position of the block in the cache. The tag is equal to the block address divided by the number of sets. So we have a cache hit when the tag of the requested block matches the tag of the block stored in cache. The block size as well as the number of sets are typically, meaning always, I don't know of any cache where it isn't the case, powers of 2. This allows to easily calculate the block address, index and tag since they are given by parts of the address as illustrated in this figure. The third question is, which block do we replace when we have a miss and all blocks in the set are occupied? Almost all processors use least recently used or some approximation of it, since real LRU is costly to implement when the associativity is high. The final question is, what happens on a write? This consists of 2 sub-questions. What happens on a write hit and what happens on a write miss? On a write hit we have 2 options. Either we write to cache as well as the lower memory levels. This is called write through. Or we only write to the cache and write to memory when the block is replaced. This is called write back. Write back caches have dirty bits that indicate if the block has been written since it was loaded in the cache. If it is set, the block needs to be written back, otherwise not, since the memory copy is still up to date. Both caches have a write buffer in order not to stall the processor on a write. The second sub-question is, what happens on a write miss? Do we place the missing block in cache? This is called write allocate. Or don't we do so, called write no allocate? Both options are being implemented. Now that we review the ABC of caches, let's review cache performance. The hit rate is simply the number of cache hits divided by the number of cache accesses. Identically, the miss rate is the number of cache misses divided by the number of cache accesses, which, by definition, is equal to 1 minus the hit rate. Cache misses can be classified into 3 categories, and each of these categories starts with a C, and therefore this classification is called the 3 Cs model. This model provides insight into the cause of the cache miss and therefore tells us what we should do to improve the hit rate. The first access to a block is always a miss, unless we do prefetching, but I will discuss prefetching later. These misses are called cold start or compulsory misses. There's not much we can do about these misses except prefetching. The second type of cache misses are capacity misses. These are misses occurring because the cache has a finite capacity and cannot contain all the data and code used by a program. The third type of cache misses are conflict misses. These are misses occurring because several blocks map and compete for the same set and are therefore replaced before they are reused. This figure shows the average miss rate of SPEC92 benchmarks for different cache sizes ranging from 1 kilobyte to 128 kilobyte. The different colors indicate the type of cache miss. In particular, the light blue color at the top indicates the reduction in miss rate when we increase the associativity from 1, meaning a direct map cache, to 2. Similarly, the pink, yellow and purple color indicate the reduction in miss rate when we go from 2 to 4, from 4 to 8 and from 8-way to fully associative respectively. In general, going from 1 to 2-way set associative has a bigger impact than going from 2 to 4-way, for example. These misses are all conflict misses, since they can be removed by increasing the cache associativity. The green area represents the miss rate due to capacity misses. They can only be reduced by increasing the cache size, as can be seen in this figure, since the green area becomes smaller when the cache size is increased. Finally, hardly visible, but here at the top is here at the bottom, there's a small black stripe that indicates the compulsory misses. The number of compulsory misses is independent of the cache size and is negligible when the cache is small, but becomes significant for larger cache sizes. In fact, when the cache size is 128 kilobyte, compulsory misses constitute about 30% of all misses. It needs to be mentioned, however, that Appendix B3 of the textbook contains newer results for SPEC2K benchmarks, where compulsory misses stay insignificant, around 1%, even for the largest cache size. The problem with using miss or hit rate as the cache performance metric is that a lower miss rate, or equivalently a higher hit rate, does not always mean higher performance. Some techniques that reduce the miss rate may actually increase other components of the memory access time. For example, increasing the associativity improves the miss rate, but often reduces the cache access time. For this reason, we will not use miss or hit rate as the cache performance metric, but the average memory access time AMAT. The AMAT is given by the hit time plus the miss rate times the miss penalty. The beauty of this equation is that it encompasses the hit time, the miss rate, as well as the miss penalty. And we immediately see that the AMAT can be improved by reducing any of these terms. I must note, however, that the AMAT is still an indirect measure of performance. Although better than miss rate, it is not a substitute for execution time. In particular because some misses may be hidden behind computations. Some students are a bit confused when they see the AMAT equation for the first time and think that the hit time should be multiplied with the hit rate. In this figure, I try to illustrate that this is not the case. The hit time is the time a memory access always takes, whether it is a hit or not. The miss penalty is the extra time taken by a miss. So hit time plus the miss penalty equals the miss time. In other words, the AMAT is also given by hit rate times hit time plus miss rate times miss time. In lesson 1.5.2, I discussed 5 basic cache optimizations. I will now quickly review them and announce a 6th basic cache optimization that is discussed in Appendix B of the textbook, but which I haven't discussed thus far. The first basic optimization is to employ larger blocks. Due to spatial locality, this typically improves the miss rate, but negatively impacts the miss penalty, since more words need to be fetched on a miss. So a trade-off must be made, and the typical block size is 32, 64 or 128 bytes. Larger blocks usually don't influence the hit time or the cache power consumption. The second basic optimization is to use a larger cache. This improves the miss rate due to fewer capacity misses. Larger caches, however, usually have a longer hit time and consume more power. The third optimization we have discussed before is higher associativity. This also reduces the miss rate, in this case because fewer conflict misses will occur. Like larger caches, however, caches of higher associativity also have a longer hit time and consume more power. The fourth basic optimization is to employ a cache hierarchy consisting of multiple cache levels. This improves the miss penalty component of the average memory access time, since we don't have to go to main memory to fetch the missing data, but often find the data in the level 2 cache. The fifth optimization discussed before is to give read misses priority over writes. So when there is a read miss and there are still pending writes in the write buffer, the read miss will be handled first, provided of course the read is from a different address. This technique also reduces the miss penalty. Finally, the sixth optimization discussed in Appendix B of the textbook is to avoid virtual to physical address translation during cache lookup. This concludes this lesson. Thanks for watching. In the next 2 lessons I will describe how virtual to physical memory address translation can be avoided during cache access. Stay tuned.